Alright, hello everyone, welcome back. I'm your friend InsXO. Today we're going to learn the next problem. They call it partitioning a set into equal sum parts. I probably read it wrong.
Partitioning a set into equal sum parts.
Partitioning a set into equal sum parts. So we're given a set of positive integers. Determine if it can be partitioned into two parts having equal sum. Well, luckily we only got two equal parts, but if he want us to make more groups of sum, that could be quite hard. So for example, we get some numbers 2, 3, 5, 6, and it can be partitioned into 2, 6 and 7, 5, which both have the sum of 8. Clarification questions. What result should be returned for the empty set? The set is guaranteed not to be an empty one. How large may the set be? Up to 50 elements. So that means we could use a recursive function. Okay, so before we look at the answer, how about we try to solve this problem by ourselves? Alright, now we got our laptop set it up. We could do some driving, so maybe we could finish some solutions for this one. For example, now if we got this set, a list of numbers. So what are we gonna do about it? We're gonna split it into two parts that will have an, let's say, equal sum. For example, 8. I don't know if this question will tell us the target number or not. Let me just read this sentence again. Giving a set of positive integers, determine if it can be partitioned into two parts having equal sum. So at the beginning, we do not know the exact number for the equal sum. We only know we're gonna split that set or split that list into two parts, and that two parts for each part of that should have an equal sum. Oh, this is tricky. Since we don't know the target, there probably have a lot of possibilities out there. For example, it could be one part of 2, then 3, 5, 6 as a group. Or it can be 2, 3, then with 5, 6 as a group. And you can do more, something like this. So there has a lot of combinations out there. As far as I know, what we could do or what we should do is to use the brute force method, which is to iterate all those possibilities and say if two group we got is equal, I mean the sum of them. All right, let me do the writing. I need to do the letter code problem for this, or I just want to do some coding. Then I did a search. I just passed the title for this question with the letter code keyword. Then I got an answer which directed me into a question that was probably just the question that we need for so that I could do the practicing. Oh, you say, for this question, I have tried it so many times in the last year, but I got all those errors, especially the 10 limit excited. That's a shame for me. Anyway, at least I tried. So for this time, can we make it better? I don't know. Let's give it a try. Yeah, at the beginning, we will use Python for sure, because for a small project or for some very small functionality, using Python is the quickest way for solving any small problems or in a high level of solution. So at the beginning, we got a list. What can we do about it? I'm going to define another function, and I'm going to call it partition. For this function, it will take the index, and it will also take the subset 1, which is a list of integer, and also the subset 2, which is also a list of integer. For the index, it's an integer. You know, for the whole problem, what we want to get is a true or false value. So, which means we're gonna start from, which means in the end, all we have to return is a Boolean value, Boolean type value. So partition, this function will return us a Boolean value, and it should start from 0, which means we have at the beginning we got a list of numbers. It must have at least one element inside of that. Then for the subset 1 at the beginning should be an empty set or an empty list, and also for the subset 2, it's also an empty list at the beginning. Now we had to actually code the partition function, and so far as I think this function will call itself over and over again. But how do it call himself? How can he call himself? Or how he call himself? That's what we should consider about next. Yeah, at the beginning, let's do some edge cases detection. For example, if that index is greater than the length of numbers, or probably greater or equal to that, then that's the edge case, which it means we should return false value, because okay, maybe that's not right. Okay, it is right. I don't care, it's right. So if it's equal to this case, we'll return false, since that's something that we don't want it to happen. For example, if the numbers equal to 2, 3, 5, 6. Then, if the index greater than that length of this list, that must means we got subset A equal to something like this. Then subset B equal to an empty set. They are definitely not equal. Let me change this for a little bit. Subset A and subset B. That's more intuitive than 1 and 2, since there are two different stuffs out there. Then, if it's not an edge case, if the sum of subset A just equal to the sum of subset B, that means we have to return true. Yeah, start to think about this. If I do it like this, index plus 1, then subset A equal to the numbers of from the index to the end, maybe from 0 to the index, then the subset B equal to numbers from that index to the end. If I do it like this, I'm going to return it for sure. If I do it like this, we can only get a part of all those possibilities. For example, 2, 3, 5, 6, and 2, 3, 5, 6, 2, 3, 5, 6. We can get only something like this. They are consecutive. They are only consecutive, but for some cases they're not consecutive. For example, this one, if you got 1, 5, 11, 5, then you got a 1, 5, 5 as a group. You would say this 5 is definitely not consecutive followed by the first 5. So this method won't work for this case. So we need to try something else. Yeah, I guess the really hard part is that, for example, for example, this one, when you selected the 2 and 5, how could you know that if you select the 2 and 5 as a group A, how do you know that 3 and 6 belong to the group 2 or the group B? How do you know that? Since those numbers could be repeated at some time, so you can't use this number, to be honest. You had to convert it into something else. For example, it could be numbers from range 0 to the length of that numbers. Let me try it out. We could print out the fake numbers and return this stuff immediately. Here we go. This is what we got from last from 0 to 3. It's corresponding to the real numbers. If we use this last, we could use like 0 and 2. Well, if all the numbers does not equal to 0 and 2, that means we could use 1 and 3. Or even better, we could do something like this, you know. If we want to take out the 0 and 2, when we take that number out, we pop it or delete that element from the original list. That's also a way for doing that. Yeah, start to think about another way of doing it. So we're gonna still use this structure, but with a little bit change out there. For example, for now, I do not care the index anymore. I just wanna get rid of it. Then for the first calling, I just treat the subset A as the whole number that we have. Then for each section, what we're gonna do is to calculate the sum for sure, and then we're gonna do a for loop for any number inside of subset A. What we do here is to put that number to subset B. And for each time, we will also create a new subset A. It's just equal to a copy of subset A. Then we're going to delete something from that stuff. So we're going to use the enumerator so that we could get the index for each number. Then we're going to delete the new subset A with the index. Alright, then we're going to give it to our function. Yeah, that's it. And for each time we call the partition, we'll get a Boolean value. So actually what I'm gonna do is to say stateless.append that state that we just get. Alright, in the end, what I'm gonna do is to return any of the stat last. So for this stat last, for each time we call the partition function, if we have a true statement, that means there must have one combination that could make two groups. The subset A and the subset B have the same value when you calculate their sum. Okay, basically this is a logic of mine, so let me try it out. Okay, we get an error since this is Python. If you somehow changed your function while you didn't change the way you call it, you get an error when you run it. But with some strong type programming language, you don't have to worry about this because the let's say the IDE will always tell you whether you did something wrong or not. Then let me just run this code again. Oh, we still get an error. So this is another problem about the Python. If you somehow did some wrong typing, you'll never know until you run it. But with strong type programming language, you will not make this kind of error. Alright, as you say, for the first test sample or test set, we have passed it. Now let's use more of that. Use example test sets. Now we got 2 of them. Let's say if we can pass all of them. Yeah, we passed all of them. How about we submit this solution? What will we get? Yeah, we got a time limit exceeded.
Time limit exceeded.
Time limit exceeded. Alright. So basically we have passed 36 of the test cases, but we get the time limit exceeded. I must say it's not that bad since I am doing this all over again, and after a whole year I still got a time exceeded. Why I say it's not too bad? Because I'm doing it from scratch and I'm still be able to write out the solution without totally based on ourselves or relay on ourselves. That's a big win. But the problem is we still got the time limit stuff. So this is not good, and this is, let's say, I just want to say this is why we need to read this book, because this book will really tell you how to solve those problems. But before I read that book, let me try if I can pass this by using some catch technique. Well, for this let's say for this algorithm, the most consuming part is the sum. So if we can somehow get that sum directly or by using some catch stuff, then we could be fine. We could probably solve this problem without facing the time limit error. You say for this function, if the subset A is equal to the subset B, that means we are calling the same function. So let me do this quickly. I'm going to, from the function tools module, import the LRU catch function, and I'm going to use it right in here. Let's make the max size equal to none, which means it will catch as many as possible. Yeah, the problem is here we are using 2 last. You know what? This catch function will not work when you have some arguments that have the last type. So you need to at least convert it into something else. For example, a tuple. We could do that. For example, tuple with this one and this one, and for each time before we use it, we do a conversion again. Subset A equal to last of subset A, and subset B equal to last of subset B. Yeah, but now everything is kind of different. Let me just run it again. Oh, we get an error since here we should give it a tuple. That's another problem with the dynamic programming language. If you do not care about that, you get an error. I mean, you have for each time after you have changed your code, you have to manually check everywhere that you have used that function. You have to do that process over and over again, totally by your own brain and by your own eyes. You have to look every part of your code to make sure that you makes no mistakes or makes no effects on those old code when you change some new code. That's the pain of dynamic programming language. Okay, so we cannot use capitalized tuple, but instead we shall use lowercase tuple. Oh, that's bad. That's also kind of the problem surrounded with dynamic programming language, because you will never know whether you did it right or not until you run it. But when you run it, it's too late. Alright, let's run it again. To say for this time we still get it working, so probably we could pass this test. Shit, we still got an error. Again, it stuck at the 36, so nothing really improved out there. So this method is not working. The catching is not working for this problem. So where I'm doing wrong, I don't know. So since we cannot actually solve this problem by ourselves, let's just do some reading and learn some new stuff from others. The dynamic programming top-down ONS time, a straightforward brute force solution is to enumerate all possible subsets S1. For each one, compute the complements S2 equal to numbers minus S1. Then check if the sum of S1 equal to the sum of S2. The problem with this approach is its performance. If there are n numbers, this solution has a complexity O(n) times 2 to the n powers. Since there are 2 to the n powers possible subsets and computing the sum of each set requires O(n) operations, this is too slow. The algorithm does not scale to the given upper limits of 50 numbers. Nevertheless, this is a new word.
Nevertheless.
Nevertheless, 尽管如此, or also. For the last time, when I do a speech, I want to say the word also.
Although.
But in the end, what I said is so. But it seems like it still got the correct meaning. The brute force idea is useful, since we notice an interesting property. If two subsets S1 and S2 from an equal sum partition, I would call it partition, but some people call it differently.
Partition.
Oh, I'm doing it right. Partition. So if two subsets S1 and S2 from an equal sum partition, then the following are true, which is the sum of S1 equal to the sum of S2, and the sum of S1 plus the sum of S2 equal to the sum of the whole numbers that we got. This means that the sum of S1 equal to the sum of S2 equal to the sum of whole numbers divided by 2. Therefore, we can reduce the problem to finding subset S1 having the sum of S equal to the total number of sum divided by 1, divided by 2. The search can be formulated using recursion. For the first element of numbers, the first element, we have two choices. The first one is do not include number 0 into S1. Try to form S1 from numbers from the second element to the end with the target as sum to the target sum S. And then we also got another way for doing that. Include the numbers 0, which is the first element, into the S1 variable. From the rest of S1 from numbers, from the second element to the end, with the target sum S minus the numbers of the first element. Here's an example of the steps we make to solve numbers 2, 3, 5, 6 with recursion depths showing up to 2. So from the S1, from the numbers with the target sum 8, try without including the first element, which is a 2, into the group A. The second, so what it does is actually to do a loop or iteration for the whole numbers that we have. And for each time, if we are in this position, we're gonna determine if we wanna include the number 2 into the first group or not. And we got the second one. We also have to do a determination to say if we wanna keep the number 3 into the first group or not. We do this over and over again. And since it's a recursion problem, we could get all those possibilities in the end. And since we have simplified the whole, problem at the beginning, like what I did is to calculate the first group and the second group, right? That's my method, and it's kind of not that smart because we had to actually maintain two lists of numbers, the group A and group B. But for this author, he did something quite genius. He found out that if we want this equation to be true, then we just have to make sure that we have a group, and that group equals to the total numbers sum divided by 2. If that's true, then this equation is true. So for this case, the author now only need to find one group and maintain one group that matches the condition. That's way genius than my method. So let's analyze the time complexity of this solution. Suppose we define a function and a subset with the index and the target sum that implements the recursion naively. What is that?
Naively.
Too young, too naive. Alright, naively, it would seem that we had to make 2 to the n powers calls of an subset since the recursion depth is n and each call makes 2 deeper calls. However, the number of possible parameter combinations that can be passed to Banner subset is only n times s, n values for index and up to s values for the target song. This means that out of the 2 to the n calls, many are redundant, so we can catch the results to achieve time complexity of only O and S. Well, how? I still remember that I used the catch technique, but I didn't get the test, the time. And it didn't save the time when I doing that. You know, we could look at the solution later, but for now, I just wanna tell you that I just found a thing. So how do we know the target sum? Since now we know that the targeted sum will always equal to the whole numbers we got, the whole sum divided by 2. So we will always know the target that we are looking for. Alright, we can implement the solution as something like this. At the first, he still used the function tools as I did. Then he defined a function called can partition with the whole numbers. But that doesn't make sense. Oh, sorry, but that's not important because this is a big function. Inside of that function, we got a smaller function, and this is a recursion function that really matters. This line is the same. We all know it's doing the catching. And then he said that the length for this function should be Banner subset, and it takes the index and the target sum. What this function does is to search for a subset of numbers which have the sum of that target sum. So at the beginning, we handle one edge cases. If the target sum equal to 0, if we had the target sum, we find a valid subset. What is that? Anyway, if the target sum is equal to 0, which means we just have to split the y. I think this is not possible. Okay, so if the target sum is equal to 0, that means we have no elements inside of the whole numbers that we got. So we will always return true. And if the target sum is less than 0, or the index is greater than the length of whole numbers, that means we are running into the end of the whole list and still couldn't find the right target. In this case, we'll just return false. Then we get the current number, the number equal to numbers of that index, inside of that index, or at that index. Search numbers index plus 1, either using the current number or without using it. So we're gonna add that indexed by 1. If we're using that as a number, we'll minus it by that number. If we do not using that number, we just ignore it and keep the original sum. Well, you at the beginning you may think, oh, this is crazy. Why he doing this? Well, because at the beginning, what he passed to the Banner subset function is half of total number of the total sum. So if he at the beginning gives us some target number, in the end, if everything works well inside of that process, then in the end the target sum will equal to 0. If it's less than 0, or if we run out of the index or the length of that list, then we'll return false. If it's just happen to equal to 0, that means that path will indeed lead us to the target sum, so we'll return true. And why here we use or? Because we just want to combine all those combinations together. We just want to know whether there has a path that matches the condition. And here we got the total number. For now, the sub function, the recursion function, is ended in this line of code. This is a parent function here. So what do we do is to first we get the total sum of all those numbers. Then we divide it. We'll try to get the half value. Something like that. If this value does not equal to 0, that means the total number cannot be divided by 2. And it can divide it by 2, but let me try to explain it again. So if this expression does not equal to 0, that means the total number cannot be divided by 2 to get an integer, but instead you will get a float number or something like that. So in that case, it's impossible to split the total sum into subsets of equal sum. Oh, sorry, that's too tedious. It should be something like this. Impossible to split it into 2 equal parts. Yeah, that's right. And in the end, we call this function. We'll get a Boolean value, and boom, the problem solved. Quite similar. Quite simple, right? I was kind of tired, so so I may not have that much energy to make a right speech anymore. Anyway, I think this is the end of today's video, and inside of this video we have tried and nerd this problem, partitioning a set into two equal sum parts. Yeah, that's right. So I hope you enjoy this video, and I'll see you guys in the next one. Bye.